in mind the motion of an object around from point to point in space. Today I start the subject of rotational motion, or as it's called, angular motion. I have in mind, for example, the rotation of this bicycle wheel. The wheel as a whole is not moving anywhere, but it's rotating around its axis. So there's rotational motion. The whole theory of rotational motion is built very closely on the theory of translational motion. In fact, every equation, every definition, every law pertaining to translational motion has its direct analog in the theory of rotational motion, with one peculiar exception that maybe I'll come to at the very end today, or also beginning on Friday. So the theory we're working on is rotational mechanics. Theory is closely analogous to translational mechanics, what we've been doing so far. In fact, one reason for studying this subject, in my view, is because it sort of reinforces everything that we learned about translational motion, to see the same basic ideas playing out in a slightly different context. Some people, Pomona College no longer teaches rotational motion at the introductory level. It's too complicated, students don't understand it or something like that, or there's too much stuff in the curriculum as it is. So get rotational mechanics out of there. Who needs it? Well, actually, we need it. It's really important. But also, I think it's a crime to take it out of the curriculum at this level, because it does have this wonderful pedagogical role of reinforcing everything that you learn about translational motion. On the other hand, it is true that I can go through the theory very quickly, because everything I'm laying out is just a direct analog to what we had for translational motion. Like regular mechanics, rotational or angular mechanics divides naturally into two parts. First of all, there's the description of rotation. That's rotational kinematics. Then there's the causes of rotation. That's rotational dynamics. So I construct exactly the same three quantities that we did for translational kinematics. There it was position, velocity, acceleration. Now it's going to be angular position, angular velocity, angular acceleration. How shall I represent the angular position or orientation of a rotating object like this? Well, I've stuck an arrow on here so that we can keep track of its orientation. And let's say that at the moment in question, the arrow is pointing like that. I need to refer this to some fixed direction, let's say straight up. So I should put an extra stick on here that's pointing straight up. Then I could just record the angle over to where it is now. And that would be a good way of specifying angular position. So here's the drawing. There's the actual position, the spot on the wheel, or the arrow, whatever fixed point on the wheel I'm using. This is the reference direction, straight up, and there's the angle theta, and I'll use angle theta to define the position, orientation, if you like, of that object. Of course, as the thing rotates around, this is going to be a function of time. That's the angular position, the quantity that I'm looking for in this business. That's exactly the same role that x of t would have played in translational motion. That's the position with respect to some fixed reference point. This is the angle with respect to some fixed reference point. No. We'll measure theta typically in radians. You don't have to, but it's a good way to do business. Remember how radian measure goes? It's the arc length, let's call it S, divided by the radius. Theta is equal to arc length over radius. That's the definition of angle in radian measure. Incidentally, as I think I mentioned before, radians are actually dimensionless because it's a ratio of a length, arc length, that's meters, to another length, radius, is also meters, so the meters cancel out. Technically, then, radians are nothing at all. It's a dimensionless unit. Still, it is a good idea in this business, I think, to mention, if you say to somebody, I'm talking about an angular position pi, to write it as pi radians, just to remind the reader that you are not talking about degrees or revolutions or something like that. So, radians are dimensionless. But I think it's a good idea to say radians whenever you write these things down. I hit this on the owl that I was, one of the owls that I was using for Friday, and the answer came out in radians, and I typed in so-and-so RAD, and it marked me wrong because radians are dimensionless. I shouldn't have put the radians in there, even though the whole statement of the problem had radians all over the place. So I changed it. So on that one, you better put in radians. You know, I think it's a good idea to say radians, even though if you come to the end of a calculation and you've got radians in there and they didn't belong in the dimensions of the answer, you know the answer came out joules radians, and it should have been a measure of energy. Rub out the radians because they don't do anything at that point. But when you're specifying an angle, I think it's a good idea. Where is pi radians, by the way? Where would the angle be? Where would the arrow be pointing if I said the angular position is pi radians? Right down, if straight up is what I'm measuring with respect to, right, because then it would be half of, all the way around. 2 pi radians would be back to the top of it. Okay, B. If this thing is rotating, then I might be interested in rate of change of the angular position, that is to say the angular velocity. That's defined in the obvious way. Omega, Greek letter omega, not a W. W has points on the bottom. Whatever. Omega of t is theta by dt, the derivative. The rate of change of the angular position, of course. What are the units of that? Radians per second, or if you prefer, just per second. Note, in the same sense that theta is arc length over radius, if I differentiate that, I would get omega is equal to ds by dt over r. The r is not changing. As this thing rotates around, the s is the thing that's changing. The arc length would be increasing if it's rotating in the clockwise sense. So the rate of change of omega would be the rate of change of the arc divided by r. But the s by dt, what would you call that? The s by dt is just actually, let's call it v sub t, the tangential velocity, isn't it right? It's the velocity The translational velocity, the ordinary kind of velocity, the translational velocity there is ds by dt. So this is vt over r. Vt is the translational tangential velocity. Let's say the tangential speed because it's directly tangent, of course. So there's a relation between the speed at which a point is moving around on that circle and the angular velocity, to wit, omega is equal to that speed divided by the radius. Nothing fancy there. It follows just from the definition of theta in radian measure. Well, if this thing is speeding up or slowing down, as it might be, then I might be interested in the angular acceleration. Right, defined in the obvious way. We use the Greek letter alpha for that. Alpha, which itself might be a function of time for all I know, is equal to the omega by dt. And that's therefore the second derivative of theta with respect to time. Angular acceleration, defined exactly the same way that ordinary acceleration is defined with respect to the ordinary velocity of the motion, only now we're talking about the angular acceleration. Note, I play exactly the same role again, or game again. Alpha is the derivative of omega, so that's dv sub t by dt. Rate of change of the tangential velocity over r. What would you call that? The rate of increase of the tangential velocity, that's just the linear or translational acceleration of the object. So let's call it a, not alpha now, a sub t over r. So there's the connection between angular acceleration and the actual linear acceleration or translational acceleration in the tangential direction. A little sweet twist in this case, however, because this thing, if it's going in a circle, this point has not only tangential acceleration associated with the fact that it's speeding up, but also centripetal acceleration. So on the diagram here, maybe I'll switch over and put in here the accelerations. This is the tangential acceleration around the edge, and then there's in addition the centripetal acceleration in toward the center because the thing's going in a circle. Also, of course, centripetal acceleration, which is v squared over r, v the tangential velocity, the velocity along the circumference. There is no other kind of velocity in this problem. If it's riding along with the wheel, then the only velocity is in the tangential direction. But acceleration, there's tangential acceleration if the thing is speeding up, but there's also centripetal acceleration. Vt squared over r, of course Vt, I decided from here, was r times omega, so this is omega squared r squared divided by r. One of the r's cancels, and I get omega squared r. So there's another way of writing the centripetal acceleration, this time in terms of the angular velocity omega. It's omega squared r, or v squared over r. Some people I've found, some physicists remember the centripetal acceleration as omega squared r, some as v squared over r. I don't know. Personally, I always think of it as v squared over r, I guess because that's the way I first encountered it, although this is, in some respects, a slightly easier formula to work with. Well, how are we doing? What is angular velocity measured in terms of, by the way? Radians per second. Angular acceleration, radians per second squared. A couple of comments. First of all, angular velocity is closely related to frequency, the number of revolutions per second, if the thing is going. I could talk about angular velocity omega, the number of radians per second, or we call it f, the frequency is the number of full revolutions per second. If somebody's selling you a machine or something, they're probably going to tell you the number of revolutions per second, the frequency that it operates at, not the angular velocity, although angular velocity is easier for physicists to work with. Angular velocity is related to frequency, which is f equals revolutions per second by, what is the connection? Let's see. I always get the 2 pi in the wrong place. Frequency is the number of revolutions per second. There are more radians, there are 2 pi radians in one revolution. So the angular velocity is going to be a larger number. It's 2 pi times the frequency. This is the number of revolutions, or the number of cycles per second. I have to multiply that by 2 pi because there are 2 pi radians in each cycle. So there's the connection between angular velocity and frequency. A second comment that I was supposed to make on that, what was that? Oh, well, let me do an example first, a stupid little example, but to show you what we mean by angular velocity. We may even have done this before, I don't know. Example, I want to just think of something or other whose rotational speed we know about and figure out what its angular velocity is. So find omega for the Earth's rotation. The Earth rotates once a day, right? So what would omega be? The angle it executes in one day is 2 pi, and I divide that by 1 day. Angle per unit time. So that's 2 pi over 1 day. Of course, if I want to get this over to seconds, a day is 24 hours, an hour is 60 minutes, and a minute is 60 seconds. So that would be the conversion over to radians per second. What is that? 2 times pi divided by 24 divided by 60 divided by 60 again is 7.27 times 10 to the minus 5th radians per second. How about that? There's the angular velocity of the Earth. Of course, the frequency of rotation of the Earth would be 1 over 1 day. So 1 over 24 times. Or that divided by 2 pi. 1.16 times 10 to the minus 5th. And that's revolutions per second. Revolutions, like radians, is a pure number, so it doesn't actually have dimensions. But you see that it's important to be able to tell the reader, was I talking about radians per second, or was I talking about revolutions per second, or was I talking about degrees per second, which nobody ever uses it in business, but you put it in principle. So, okay, the second comment I wanted to make for a rotating object, the angular velocity is the same for all points on that object. For example, in this case, the angular velocity of the Earth is 7.27 times 10 to the minus 5th radians per second for somebody standing on the North Pole, for somebody on the equator, for somebody 20 miles inside the Earth's crust. I don't care. It's the same for the whole object. as long as it's a rigid object rotating all at once. The linear velocity, the translational velocity, of course, will depend entirely on where you are. For example, on that bicycle wheel there, let's look at that case, so the three-dimensional aspect of it isn't a problem. If this thing is rotating around at angular velocity omega, and I say, what is the velocity, the actual linear velocity or translational velocity of a point out at a distance r from the center, what would that be? It's going to be 0 if it's right in at the center. It's going to be a maximum if it's out at the perimeter. And at any point inside, it's going to be somewhere in between. What is the actual velocity at that point? V, well, it's given by the formula up here. V is equal to omega times r. This is for something that's not all the way out at the full radius, but it's still the case that the angular velocity is the same for all points on that thing, but the linear velocity, the translational velocity, depends on how far you are out from the axle, in proportion to how far you are from the axle. Make sense? Okay. How about what was the next example that we did in the case of translational motion? We looked at the simplest, sort of non-trivial case of motion. That was motion at constant acceleration. You can say motion at constant velocity, but there's not much meat in that. So let's go similarly to rotation at constant angular acceleration. See what can be said about it. Rotation at constant angular acceleration, so something is rotating at angular acceleration alpha, and let's say it starts at angular position theta 0 at time t equals 0, and with initial angular velocity omega 0. What would its orientation be at some time later? You tell me. What would the general formula be? It starts out at angular velocity of theta 0. Its initial angular velocity was omega 0, and it's going at constant angular acceleration alpha. Can anybody tell me what the formula is going to be? Not dredging that up from memory, but just think what it's got to be, because this is exactly the same problem that we confronted with translational motion. Only, I'm going to just use a dictionary to translate
theta 0
x
plus
to theta, v to omega, and alpha to...
So theta 0 plus
It would be the initial angle
omega 0t
plus the amount it would have rotated if it had kept going at that initial angular velocity. And now, how much further will it go because of the angular acceleration?
alpha t squared.
Half alpha t squared.
Yeah.
Like that. This is for constant angular acceleration only. How do we put that together? Well, it's exactly like x of t equals x0 plus v0 times t plus 1/2 a t squared for translational motion. In fact, I don't think that I need to derive this formula, because every step in the derivation would be identical to the step in the derivation that we did back here The only difference is we would be using thetas instead of x's and omegas instead of v's and alphas instead of a's, but the argument is identical word for word. What would the angular velocity as a function of time be in the case of constant acceleration? I could get it by differentiating this, of course. It would give me omega 0 plus alpha times t. Differentiating to t, I get 2 alpha. This is exactly like the old formula. V of t equals v0 plus at if you were going at constant translational motion, constant acceleration. There's even that other formula that gets the t out of there. What was that? 2a times x minus x0 is equal to v final squared minus v initial squared. V, let's just call it v, the v that prevails when x is x. That also would have its analogous formula for rotational motion. What would it look like? 2 alpha times theta minus theta 0 is equal to omega squared minus omega 0 squared. So that also is true, just by direct analogy with the translational case. I want to emphasize as much as I can the direct parallel with translational motion, because actually, probably on Friday or maybe next Wednesday, I'll give you a dictionary, just a complete dictionary for how you translate everything back and forth between the rotational case and the translational case. There's nothing new that you have to learn in as far as the actual manipulations of the equations. But in dynamics, there is a new twist. So let's move from kinematics now over to rotational dynamics, the causes of rotation. Let's see, in the case of translational motion, I had Newton's 3 laws. Rather analogous structure here. 1, if something's already rotating and no force is acting on it, then it's going to keep on rotating. With the same angular velocity. Some force. Of course, in practice, there's always some friction in there, although one nice thing about rotational motion is it can be very much closer to frictionless than translational motion can. So if I do the demonstration with this, Newton's first law, if you want to call it that, I'll put it in quotations because we're talking about rotations now, but Newton's first law is much more plausible for the rotating wheel, I think, than it is for a moving brick or something like that, because if I try to demonstrate it with a moving brick, you know, the fact of the matter is, I think quickly comes to rest, and it seems like it's not true. But for a rotating wheel, this is very close to being frictionless motion, and so it's actually a cleaner system than the, for illustrating Newton's first law. Remember, for translational motion, I had to get out the air track and do it on the air track. That was the way of getting rid of the friction. Here, the bearings on that thing do a pretty good job without an air track at all. Let's see. An object keeps rotating with the same omega unless acted on by some force. This you might call Newton's first law. I don't know that Newton ever did this, but Newton's first law of rotation. How about the second law? Which, just as in the translational case, This is where all the action is in rotational mechanics. Newton's second law, that's as F equals ma. It tells you, in the translation case, it tells you what happens when you do apply a force. If you do apply a force, you're going to get an angular acceleration. The question is, if you do, what angular acceleration are you going to get? This is a much more subtle problem, because, stop to think about it, it depends not only on how big that force is, but where that force is applied and in what direction is applied. So, I'm going to illustrate this in a second. Here's what I have in mind. Here's the rotating wheel there, and I ask you first, suppose that I pulled on that wheel with a force that went like that. How do I mean that? Let's call this F1. Suppose that I took a piece of string and attached it to the wheel right in there at the axle, and then I pull on the string. How much is it going to rotate?
0.
Not at all, right? How about if I took the string and glued it on down here, a little ways away from the center, and pulled like that, F2. Can you imagine me doing that? I thought of getting a piece of string and actually doing this, but it would take me too long to tie it on. But imagine that I tied the string on there, and now I pull straight down on it. How much is it going to rotate? Not at all. I pull harder, still doesn't rotate. No good. So those two forces, even though I'm actually acting on this wheel with a force, it doesn't rotate at all. In fact, what's the general rule? Evidently, any force that acts right through the axle is not going to cause this thing to rotate. In fact, for a given force, you will get the most rotation, I think it's clear, if it acts perpendicular to a radius to the center. Isn't that right? So if I really wanted to get the most bang for my money, I might take that force and act it like this. Here's F3, like that, perpendicular to the radius. Then it just feels to me like that's going to produce quite a lot of rotation. But if it's acting straight through the radius, straight along a radial line, it won't produce any rotation. I should be writing this stuff down. What I'm trying to do is warn you about the features that are going to go into answering this question. Then I'll write down what the answer is. Forces. Forces that act along radial lines do nothing. You can take a force like this and pull in that direction. It's not going to tend to rotate the thing. Most the force that's most effective in producing a rotation if it acts perpendicular to a radial line. Moreover, the further out that force acts, the more effective it's going to be. Isn't that right? If I attach my string out at the radius and full radius and pull with a force exactly the same as this one here, I'm going to get more rotation. Isn't that right? That's why you stick the doorknob as far as possible from the hinges, because the further out the force acts, the more effective it is in producing rotation. If you stuck the doorknob right in there next to the hinge, you'd have a hard time opening the door, right? But you put it way out here, then it's more effective in producing the rotation. So, moreover, so what is all this telling us? It tells us that the amount of rotation you're going to get, the angular acceleration you're going to get, depends not only on the magnitude of the force, but also the direction it acts and where it acts. The further out, the better. The direction perpendicular to a radius is better. How are we going to assemble all of that information? I like to think of it like this. Here's the wheel. Now let's get us a force. Here's the axle of the wheel, the axis of rotation. And let's say that I apply a force at this point here and in this direction, like that. So there's my force. And I want to measure of how effective that is in producing rotation. What I do is extend this line back. So I've constructed what you might call the line of force. Which is just a line along which that force acts, but extended all the way back. And now, let me define this distance here, which the distance from the axle to the line along which the force acts. Of course, by that I mean the perpendicular distance here. We'll call that L, and it's known in the business as the lever arm. So, lever arm is the distance from the axle to the line along which the force acts. Is it clear that the larger the lever arm is, the more effective that force is in producing rotation? Suppose, for instance, that the force actually acted along a radial line passing right through the origin. What would the lever arm be in that case? 0, isn't that right? Because then the line of force would pass right through the origin, and you would get no rotation at all from that. The effectiveness of a force in producing rotation is a product of the force itself, the magnitude of the force, times the lever arm. We call that torque. And this book, most books use the Greek letter tau for that. Is equal to the force times the lever arm measures larger the torque, the more angular acceleration you're going to get. Indeed, I can now write down for you Newton's second law for rotations. The thing that plays the role of F is tau. But it's not just an obvious trivial switch, as it was for kinematics. Rotational kinematics is trivial. It's just a carbon copy of translational kinematics. Dynamics, not so. The first sign of that is that the thing that's producing rotation is not force directly, but torque. So the second law reads, for rotations, tau, think playing the role of F, is equal to something or other times alpha, the thing that plays the role of acceleration. Tau is equal, it would have been F equals, I'll put it down here in parentheses, ma. Now I need something that plays the role of mass. The rotational inertia, if you like. We call it I. Or for historical reasons, it's not called rotational inertia. Some books are trying to switch over to using that language, but most physicists are used to calling it moment of inertia. It plays the role of mass. But it's not just mass itself. It tells you how hard it is to get this thing rotating. Let's think what that's going to depend on in sort of the same way that we thought how to introduce tau, how to define the torque, the effectiveness of the force in producing rotation. What, in the same sense, is the inertia? It depends not only on the mass, but also on where that mass is located. Why is that? Think about it. I got some mass on this wheel. Suppose that I packed all that mass in, well, I can't move this stuff around. Suppose I got some extra mass I'm going to stick on here, a lump of clay, and I pack that on right in close to the axle, Then it's still pretty easy to rotate this thing. But suppose that I took that same lump of clay and smeared it out along the axle, way out there, along the rim. Then it would be quite a lot harder to rotate the thing. Do you believe that? I'm hoping that your intuitions are consistent with that. If you take a certain amount of mass and pack it in close to the axle, then it's still easy to rotate. The moment of inertia is fairly small. But if you stick that same mass way out at the rim, then it's a lot harder to rotate. We have read a bicycle wheel like this, and then another bicycle wheel that has, actually the two have the same mass. I guess this one's got an extra weight in the center, but the other one has a lead weight all the way around the outside. You just feel it. It's tough to rotate the one with the lead weight out there. The one where the same amount of mass is in toward the center rotates pretty freely. So the moment of inertia depends not only on what the total mass is, but where it's located. So if you stick it in close to the axle, it doesn't contribute much. If you put it out at the periphery, it does contribute a lot. I'll tell you what the formula for the moment of inertia is. Actually, what I'm trying to do today is get all my cards on the table. The proof of the second law and the formula for the moment of inertia. Today I'm trying to make it plausible, but the proof will come next week, actually. Moment of inertia is actually, if you've got a lump of, a bunch of lumps of mass distributed around, it's Ri squared, the square of the distance from the axis to the lump M. So it not only depends on the mass, but it depends on how far it is from the center, and it depends very sharply on how far it is from the center, like the square of the radius. So you put that mass out twice as far, the moment of inertia gets 4 times as large. If I had the uniformly distributed mass, this would become an integral of r squared dm, in the same sense that we use that sort of notation for center of mass. And indeed, on Friday, I'm going to do a bunch of examples of calculating moment of inertia from those two formulas. Let me end by mentioning the one law of physics, one law of translational motion that you will not encounter in rotational dynamics. That is Newton's third law. That says the force, if one object exerts a force on another object, the other object exerts an equal and opposite force back on the first. There is no analogous law for rotations. It is not the case that if A exerts a torque on B, B exerts an equal and opposite torque on A. In fact, it can't be. You can think of an example yourself. Suppose that I had a spinning flywheel here, maybe a grindstone or something, that's rotating around like that. And I bring up next to it, I'm holding these on axles so that they rotating about an axle. I bring up next to it a smaller wheel like that that's initially at rest. What's going to happen? Sparks fly, and pretty soon this one is rotating too. But while that's happening, what are the forces? The force of the big wheel on the little wheel is F1. The force of the little wheel on the big one is minus F1, equal and opposite. What is the torque on the little wheel? Well, that would be F1 times R1, the lever arm for R1. What is the torque on the big wheel? That would be F2, F2 is minus F1 times R2. Are those two equal? The forces must be equal by Newton's second law, Newton's third law, but the radii are not equal. So the torques are not equal. I'm sorry. There just is no analog to Newton's third law for torque. Everything